if we have data organized in a data frame, and typically we have the variables in columns. Now for machine learning, we are very much interested in finding out what relationships are there between the columns. And so we use some kind of quantification to find out what each pair provides. And one way of quantifying it is to take each pair of columns in a data frame and calculate the correlation coefficient, which in total, calculated over all possible pairs, yields the correlation matrix. So I'm going to use that as an example to show how interrelationships between all columns in a data frame can be calculated and visualized. Of course, we have to keep in mind that using cross-correlation or correlation for short is just one example, and that, of course, any bivariate measure can be used to set up such an interrelation matrix for a data frame. Importantly, because even though it's nice to have data organized in a pandas data frame, when the data sets become big, we need to go for speed, and thus we want to use Numpy arrays. So I'll show you how to convert a pandas data frame into a Numpy array and obtain correlation matrix from there. So let's start with this prepared code here, where I read in a data set which is patients in CSV format, and if I display the first 5 rows, we can see that it has 7 columns, of which the first 5 are numeric and the last 2 are categorical, saying either yes or no for a certain characterization. So within a data frame, it's very easy to get the correlation matrix, so all possible interrelationships quantified by the Pearson correlation coefficient, if you just use the function cor, and here's the result. So notably, you see that the outcome is a square matrix. You have the names of the columns as the names of the rows and the names of the columns now in that output. And you can see the diagonal elements are all 1. Every column compared with itself gives you maximal correlation or identity, which is 1. And it's a symmetric matrix, so comparing age with height is the same as comparing height with age. So let's convert this to a Numpy array now. The easiest way to get a Numpy array, so the data frame as Numpy array, is to apply to it a function to Numpy without any further arguments. And if we check the shape of that result, we can see that it contains 100 rows and 7 columns. Let's now import the functionality to calculate the correlation coefficient from Numpy. So import, and the name of that function is called coef. So we can use that, and we want to apply it to only specific columns. If we go back, first 5 columns were okay, but 6 and 7 are categorical, so we want to avoid them. So the way to do it, I define the number of columns that I want to consider. So it's the first 5 columns, so up to 5. And then one thing that we need to know is that to calculate the correlation coefficients using coef, all the numbers that come in must be of the type floating point or decimal numbers. So let's do that. Let's convert everything to floating point numbers, whatever is in that array now. Let's select. So we want, of course, all rows, but let's take columns only up to 5, so the first 5 columns, and convert them to floating point by saying s-type and providing the argument float. So that will give us something that is a Numpy array, but of course only floating point because of that conversion. And then once we have it, then we can use the function core_f and apply it to that floating point array. With another thing that we need to consider, if you use that core_f function, what you need to know is, let's have a look at the options. There is a keyword argument called row_var, meaning treat rows as a variable, and it's set true by default. So we want to overcome that because we want to have the columns treated as variables. So we actually need to set row_var equal to false. And once we do that, we can assign, say, data frame correlation, just to give it a name, and then we can see the outcome of this after we execute the code. And it's numerically identical to what we had before in this data frame correlation. So this is the correlation matrix. It contains all possible relationships between columns that we have specified. So it's a 5x5 matrix. And what we need to do before we visualize it, we want to replace the ones on the diagonal with a 0. The reason being that 1 is a very large number compared to some of those correlations that are in the array, which is 0.08, so it's much smaller. So in that case, the 1 will very much dominate anything that we do with it. For example, if we plot it, that 1 will of course be the dominant entry. Because it's trivial, we want to ignore it. So one way to ignore it is to import a function from Numpy, which is fill diagonal, and we can use fill diagonal applied to our correlation matrix, which is contained in dfcor, and we have to specify what we want to have there. Instead of ones, we want to have zeros. So just putting in 0 as a second argument will do that. If you like, we can also check that, and you have the same correlation matrix as before, but now the diagonals are all 0. So with these couple of manipulations, we are now ready to do our heat map. So let's see the correlation matrix, and we do that as usual using subplots. And then we have an axis, a coordinate system called ax, and we use the function imshow, where we only need to provide the array that we want to have visualized. So if we do that, we get some output, and if you think that looks ugly, I agree. We can change the coloring by picking a color map. You can Google matplotlib color map to find all the options there are. One thing that is widely used is blue, white, red. If you use blue, white, red, so the minimum will be dark blue, the maximum will be dark red, and in between it will get lighter and lighter towards the middle, where it's not going to have any color but be white, so to speak. So if we replace it, put semicolon at the end, now we have a much nicer way of visualizing the correlation coefficients, which is what we have. The only thing that we miss is that interpretation of what does it mean to be dark blue or dark red. So what are the extrema shown in this? And the way to do it is to assign the output of that function to an object, which is called anything but im for image maybe, and then add to that figure using a colon, using a period, a color bar, and say that you want to have the color bar that corresponds to this image. And if I again suppress output here with a semicolon, we have a nice visualization of that correlation matrix for the first 5 columns of the data frame that represents our data. We can now go and interpret it. You can see that the diagonals, the 0 is the dark blue, and these are the smallest numbers, so all correlations in this case are positive, and the largest are here in light red and dark red, so the strongest correlation is between columns of index 1 and 2. And if we go back up, that is height and weight. So height and weight is strongly correlated. It's on the order of 0.7. And the second strongest positive correlation is between systolic and diastolic blood pressure.